very much for coming. It's hard to compete with Venkat doing his show in another room. I will try. I will try to show you something new, maybe, about Java. So my name is Ivan. I took the very early train from London today to be on time for my talk. Currently I'm working as a team lead at Synthesized company in London, and also I'm currently a lecturer at Northeastern University London. Before that, I taught people in various universities, primarily Java and computer science. At Synthesized, we are providing ways to anonymize data, for companies to anonymize data, to generate realistically looking data for testing. But this talk is not, and we are using Java, we are using Kotlin actually for that, to work with databases. But this talk actually was inspired by my experience as a teacher. So what does it take to make a lecture course on Java, for example? You need to prepare like a lengthy talk each week for 14 consecutive weeks. I don't feel like drawing on the board because you need to prepare lots of pictures, lots of illustrations. And I want to make slides as code. Actually, throughout my career, I decided that it's best not to use software like PowerPoint, but rather code slides in plain text. And I have a blog post on this. And finally, as a software developer, and every software developer is a lazy person, right? I asked myself, is it possible for the slides to draw themselves? In particular, I wanted to demonstrate my students how hash table works in Java. Who knows how hash table works in Java? Most of you, yeah, everybody. Yeah, but for students, you need to draw this, right? And it's not an easy task. So I just wondered, can it be somehow automated? Well, who never heard about GraphViz before, GraphViz software before? Yeah, some fraction of you, but otherwise it's quite well known. First of all, it's very ancient. It's older than Java itself. On the other hand, it's being very actively developed until like recent time. So this is very old and very stable and very actively developed software. And the idea is that it provides a DSL, a domain-specific language called DOT, where you define the graph, and it provides a program utility which converts this DSL into visual representation. So here, as you can see, I just provided nodes and links in the graph, but I never bothered about how to put it on a plane, how to visualize it. That's the work for DOT software. So I looked for a way to visualize Java objects in DOT format, and I Googled, I found quite an ancient page. So it's 20 years old like today, from John Hamer, my colleague, a teacher. He used to teach in New Zealand at that time. And in 2004, it's hard to imagine, but in 2004, we had no GitHub, and there was no Maven Central. So what all that he could do is just upload a Java file on his personal web page in the university and say that it's free to use under GPL license. So 15 years later, I found this web page. I downloaded this Java file, and it worked for me. So it's like, I think it's a perfect illustration of how stable Java is, how backward compatible Java is actually. So I prepared some pictures using it for my lectures, and in 2020, in the very beginning of COVID, two students under my supervision. They put it on GitHub. They organized Maven release to Maven Central, CI tests, refactoring, etc., etc. And well, surprisingly for me, although this tool is, well, quite narrow, quite specific tool, it was recognized and by community. Now it has more than about 300 stars on GitHub. But that's not the end of the story. So about that time, 2020, Java 8 was no longer a de facto standard for people. And with newer versions of Java came a limitation of reflection. So if you are going to introspect standard classes from standard library using reflection, you need to add specific keys to your command line, and anyway, it can be tricky. Also, using reflection imposed some problems for us for testing, because we wanted to write tests for our software, but for example, getDeclaredFields method in reflection API doesn't guarantee us the ordering of the fields. So from one run to another run, it can provide the list of fields in different order. So it made us, so it was difficult to write tests for the visualizer in this case. So we decided to look at OpenJDK JOL library. Who heard something about JOL before? Not many people, but some people. So JOL is actually a very low-level tool, primarily for performance engineers, which hacks into the structure of Java objects and reveals their internals, actually what on byte level, I would say. In order to do this, JOL uses black magic, unsafe, and other things. And good news, as it's a part of OpenJDK, we can rely on its support in the future. So JOL doesn't need reflection. JOL doesn't need add opens in order to introspect objects in Java memory, to get their fields, field values, etc., etc. So I asked Alexey Shepelov, the maintainer of JOL, to open some APIs for us to make them public. And Alexey proposed something else. He told me that he don't want to increase the surface of the API of JOL, but he would rather want our visualizer to be a part of the JOL. By the way, yeah, the example JOL layout, the example JOL output. So that's the main use case of JOL usage. So if you want, for example, to see how HashMap works in Java, so how HashMap object looks like internally, you can run JOL and you get this report, this dump. So you see like bytes up to byte the headers of the object, then all the fields inside the object, and all the values of these fields inside the object. So actually, it's very precise introspection. And Alexey wrote a blog post called Java Objects Inside Out. And you can also Google, I think he had a couple of presentations at conferences about it. But his work was focused on the layout of object itself. The mark word, the class word, the field alignments, how many bytes exactly does it take for to lay out a given object, a given class in memory, while Java Visualizer focuses on data structures layouts, other form of visualization. So this, although I can recommend you this blog post as well, my talk will be completely different. Things in open source are not being done quickly, as you know. So it took some time to properly merge our visualizer into JOL library. And although it is on the main branch since February of this year, there was no still new release of JOL. So if you want to use LJV, lightweight Java visualizer inside JOL, you need to build the snapshot version yourself. But as soon as there will be version 0.19, it will be possible just to use it as a Maven dependency. So I think it's time to show how it works. Like, did you ever wonder how a stream looks like? What objects are there and how are they linked together? So in order to do this, we can construct an object to introspect. So it's like, let's build a stream out of the list. So let's create an immutable list, then create a stream, then put some map, then put some filter. And then we get a stream of integer, which is an object, right? Which we want to visualize. Then we are going to prepare an LJV object. LJV belongs to org.openjdk.jol. And then, if we look here, LJV has this method called drawGraph. DrawGraph produces a string in dot format, and there is some magic to invoke the visualizer itself. So let's run it, and let's see what we have. So on the left panel, we have dot output. On the right panel, we have the visualization. So let me show it, in another tab of browser. So this is how it looks like. So we can see that there is an immutable list here. This is immutable list n class. There is a split iterator at the beginning of the stream. There are some reference pipelines for map and for filter. And there are predicate and the mapping function, which are lambdas, but using the introspection, there is little we can know about lambdas itself. So they are just plain objects here. So this is how it looks like. So in this talk, I want to demonstrate to you some findings or some illustrations I prepared for various slides, for various lectures. And the outline is the following. So we will start with strings and primitive wrappers. Then we are going to cover queues and decks in Java, then map and concurrent map. And then, if we have time, navigable map and concurrent navigable map. And please note, there will be no manually adjusted images on this presentation. All the diagrams in these presentations are dumped as is from JOL output. And actually, the source code is available on GitHub. There will be a link in the end of the presentation. So this is code, and all this is done automatically, actually. OK, let's start with string. Everybody knows string. It's most widely used class in Java, right? So what will we see if we try to visualize hello string in Java? Well, it heavily depends on the version, right? So in ancient version, like Java 6, we will have three fields in the header of string. Then there will be only one field, hash. Then there will be two fields, coder and hash. And then there will be, again, three fields. So at the first glance, it looks like an evolution went wrong for string class. But actually, it's not. There were reasons for doing these changes in string. So how it started? If in Java 6, we call a split method on some long string, we will get in the visualizer the following picture. So as we can see, there's an array of strings, about a dozen strings, but all of them, they are sharing the same buffer, the same array of characters. So how do they know which segment of this array they are looking at? They are using this offset and count fields in the string. So this may look like a bright idea, because split is going to be fast operation, right? We're not reallocating buffer. But there are problems. If we're going to visualize this object, we will get in Java 6, we will get this picture. Like here, we need only 3 first characters. But in Java 6, string will hold the whole buffer. And there is no way to access characters in this buffer if we don't have any other string looking at it. So this is clearly a memory leak. So starting from Java 7, it was decided to abandon this practice. So in Java 8, for example, you have only one field, hash, for the string, which is 0 until you calculate the hash on string. When you calculate the hash on string, it fills it with some value, and then it reuses it each time you're asking for a hash. So now, a split operation is no longer a fast one, but we have separate strings and separate buffers for each extracted substring, I would say. And if we will do this test on Java version 8, we will get just a small buffer of this with 3 first characters. So yeah, this is definitely better. But it's not the end of the story. So as you might remember, Java used to use character char, array of char, to hold strings. In the very beginning, it was decided that Java is going to support Unicode, so all the alphabets, so Latin alphabet, Cyrillic alphabet, and char is 16 bits, takes 16 bits, right? So it is able to, well, represent most of the characters of most of the alphabets. Well, but practice shown that in most cases, still, Latin alphabet is being used in strings. So starting from Java 9, and it was a huge improvement in Java 9, actually, they decided to use a byte, array of bytes for string representation. And you see an additional, we have an additional field here called coder. Its type is byte also. And now we have only 2 coders. First one is for Latin, Latin characters. So if we create a string and it understands that it contains only Latin characters, so representable by 1 byte. So it uses coder 0, and string is actually 2 times shorter than it used to be in Java 8. So, well, if you, well, I remember when we migrated from Java 8 to Java 11, we just saw a dramatic decrease of heap consumption just because of these compacted strings. So it's like optimization which comes for free with newer versions of Java. And this is not the end of the story. So you remember there is this hash field, always, and it has always been here, the hash field. And its purpose is to cache the value of string hash. So until we calculate the hash of string, its value is 0, right? When we put a string into a hash map, we calculate hash, but it's not a free operation. It's big O of n of the string size. So we calculate it once and put it to this field. But the problem is that there are non-empty strings in Java which have a zero hash. And actually, you can construct, Java string hash is not cryptographic one, so you can construct lots of collisions. I will demonstrate it a bit later. And you also can generate lots of strings with zero hash. And this can unfortunately be used for attacks, for DOS attacks. So if you have a very long string with zero hash, it will work like this. So its hash is 0, so each time we want to calculate its hash, it's being recalculated. So we have performance loss. So this is why in modern Java, starting from version 13, we have hash is 0 in string header. And for now, this is the end of the story. So this is how we ended up with the three fields in string header again. Although they are not integer, one of it is Boolean, another one is byte. So this is how strings look like today. Another example. Look at this code. So we created a string, and now we are doing some stupid things, right? So we are creating a new string using x as argument of constructor. We are creating a new string from char array, which we built from x. Then we concatenate with empty string and using plus and using concat method. So all these operations should give us the same value x, right? In theory. In practice, before Java 15, it looked like this. For value 0, it's x. For value 1, you see it's a new string, but it reuses the buffer. So at least some optimization. So it's still not prohibited for two strings to share the same buffer if they are equal to each other. But according to the contract of new operator, we must create a new object each time. So new operator must create new object. But in this scenario, it behaves well, right? So it reuses the buffer. It just creates the new header. All the other scenarios, they perform not perfectly before Java 15. This was fixed in Java version 16. And now, if we try to visualize this array once again, we'll see a much better picture. Actually, every call which does not produce a new string, which produces the same equal string, will create a new object if Java language specification requires us to create a new object. For example, it requires us to create a new string on concatenation operation. So it creates a new object, but this object reuses the buffer. So this is an optimization which appeared in, quite recent version of Java. There is also string interning. There is an intern method on the string, and when we call it, we will actually have the same string. No matter how we create it, it will be the same string object, and it all boils down to the string object in internal string pool in Java heap. But as Alexey Shepelov says, this intern method is not intended for usage of users of the platform. It's intended for internal use of those who create Java libraries. String deduplication situation when we have many strings which are equal to each other is a good practice, but not via intern method. So interim conclusions about strings. Switch to newer versions of Java. Strings are getting better and better, just for free. You're upgrading your Java and you get better performance for free. And in case of performance due to memory overhead, in standard Java library, many things have been already improved, but string deduplication is one of the techniques you might be wanting to use, but not through intern method. And a couple of links, they will be available like in the end on GitHub. What else do we have similar to strings in Java? Immutable objects. These are primitive wrappers, of course. And if we try to create this array, so actually it's 4 instances of 42 and minus 42, minus 42. If we try to visualize this, we will see this picture. So I believe that for many of you, it's quite expectable, right? Because we know that in order not to hold too many different objects in memory holding the same integer value, Java deduplicates. Java deduplicates values, and by default, it deduplicates them in this range from 128 to 127. So small integer values, they are automatically deduplicated using boxing and unboxing, and well, you must not worry about using boxing and wrappers if you are dealing with really small numbers, or if you are dealing with small amount of numbers. But there can be problems if you need to wrap big numbers which fall out of the range of caching. For example, big negative integer will always give the new object with each boxing operation. So in this scenario, what can be done? Use primitive arrays. Use libraries like fast2til or Eclipse collections, which can deal with, like, there can be int list, the list of primitives, without which is working with primitive values without boxing or unboxing. Or I think we should wait for Project Valhalla. By the way, there will be a talk about Project Valhalla next in this room, and one of its outcomes must be ability to write this list of int, to use primitives as generic parameters. But until we don't have Valhalla, please remember about boxing and overhead of boxing operations, memory overhead of boxing operations. Okay, that's it for primitive, simple data structures. Let's look at something more interesting. Queues. Again, let's prepare our LJV visualizer in this way and create a linked list. When we create linked list and populate it with some value and we run it and we see a picture which is classic one, I think everybody on computer science courses saw this picture. It's illustration of double linked list, and its implementation in Java standard library is provided via linked list class. But my favorite tweet from Josh Bloch, the author of Effective Java, is this one. Does anyone actually use linked list? I wrote it and I never use it. What's the problem? Despite good theoretical qualities, big O of 1 for addition by the either end and stuff, we have memory overhead here because linked list is actually boxing every value here. You see set treat as primitive integer class. If I select this option on LJV, it visualizes 1 and 2 and 3 and 4 like primitives, like exact values of these fields. But if I comment out this line, there will be more complex graph because actually node contains a reference to integer, which in turn boxes the primitive. So we have big memory overhead here. We have memory fragmentation here because these nodes, they can be created in various parts of Java heap. We cannot take advantage of CPU caching, so this is why linked list is inferior to array list when it comes to working with list. But you may ask, and what about queues? So a data structure where we add to one end and extract from the other end. For this, linked list must work well, right? Unlike an array where we have to shift elements. Well, in Java we have array deck, and we can visualize it like this. So let's create an array deck and fill 3 elements. So array deck looks very similar to array list, actually. It has a buffer. This buffer has some capacity, which is like bigger than the number of elements in this buffer. So here we have an array deck of 4. So it's there are 5 elements here. In this buffer, we created 3 elements and put it to this buffer. What happens when we extract an element, like extract 2 elements? So instead of shifting something, array deck just notices tail and head. So it just substitutes the value of elements with nulls and says now the head is element number 2. When we add more elements to array deck, they are being added to the end of the buffer and then to the beginning of the buffer because we have some space in the beginning. Of course, at some point, we will need to reallocate the buffer, to copy the buffer as it comes with array list. But if it's done properly, if we are growing exponentially each time, say doubling the number of elements, it won't be a problem on the long run. And when our queue is stable, when we're adding elements with a similar speed, with the same speed with removing elements, it's going to work really fast without need to allocate elements, link, unlink elements, and linked list. So the truth is that, well, indeed, there is linked list class in Java library, but we don't need it. Just by replacing linked lists with array lists and array decks in your code, you can improve performance. There is another interesting data structure which is visualized well by LJV. It's priority queue. So priority queue is actually a queue where you don't put an element to an end of the queue, but it's being inserted into the queue according to its priority. So again, we can set up the visualization in this way. Let's create an array of integers. Let's shuffle it. And then let's set up a priority queue with this array. So as we can see here, elements in, again, this data structure looks very like an array list and array deck. So it's just an array and it's just a header here. But elements looks like sorted, but not quite sorted here. Because, and somebody here is like already going to tell, because it's binary min heap structure. It's binary min heap. The trick of binary min heap structure is that it has very simple invariant. Actually, this one. So 0 is less than 6 and 1. 6 is less than 7 and 10. And 1, in turn, is less than 5 and 2. So we are not bothering with accurate sorting of all the elements in the binary min heap. But it's just approximately sorted. They are just approximately sorted so that this invariant holds. And this leads to the following. When we extract elements from the binary min heap, we are pulling the first element from this queue, and then we are shifting all the elements, but we are doing this like the following way. So we're selecting between 6 and 1 between children of 0, two children of 0 are 6 and 1, we're selecting the minimum, so that's 1. Then we're selecting minimum element, like minimum child for 1, and so on and so forth, so that this gap actually doubles with each step. And as gap doubles with each step, this means that the operation of extracting a value from binary min heap has logarithmic complexity. This means that it's very efficient, very efficient. Yeah, we can repeat it, and we see that with each extraction, there are less and less elements in our priority queue, and each operation leads to shifting of logarithm of n elements in the queue. What if we want a concurrent lock-free queue and deck? Because all of this works well in a single thread. What if we want to operate a queue or a deck or a stack in a multi-threaded environment, and we don't want to use locks? For that, in Java standard library, we have concurrent linked queue and concurrent linked deck. And if you visualize them, we will see that they are nothing more but a classic linked list and double linked list. But the trick here is not in the data structure itself. The trick here is in algorithms, in methods of adding and removing elements. These are quite complicated methods using compare and swap operations. There is like a big science under the hood, and this is not visible in this kind of visualization. So, what are conclusions about queues in Java? So, a linked list is useless. If you are still using linked list, please don't. Please replace it with array list, array deck, priority queue when appropriate, and you will instantly get better performance. Arrays are a very powerful foundation for building efficient data structures. So you may think that array is the most primitive data structure in like in computer science, but they are really extremely powerful because in arrays we have data locality. It's put like together. It's we can utilize CPU caching when we read data from arrays. So they are very efficient actually. If thread safety and non-blocking behavior are needed, the idea of a linked list starts working again in concurrent linked queue, concurrent linked deck. So of course, there you will have all the problems with memory overhead, but you are paying this price for concurrency, for efficient concurrency. It's always like that. You have to pay price for new features. Okay, let's move on to maps. Map and concurrent map. So yeah, this is classic. Everybody knows, so everybody must know how HashMap works in Java, because it's one of the most prominent questions at Java developers interview, job interview, right? Tell me how HashMap works. So this is the picture which I wanted to, the creation of which I wanted to automate for my lectures, and yeah, I think it's quite clear. So Java HashMap uses chaining as a collision resolution strategy. So we have an array of buckets. When we calculate hash, we calculate a bucket number. And then in this bucket number, we're looking for some node. And if there are no collisions, there will be one node. If there are collisions, we will have a tiny linked list in which we will have to look sequentially with a big O of n complexity. But when everything's good, we have small number of collisions, and it all works well with big O of 1 complexity. But as we know, Java string hash is not cryptographic. So it's quite easy to create a huge number of collisions for strings. So let's try to generate them, and let's see what happens. So if we generate a number of strings with the same hash, so as you can see, all these strings, there are 6 of them, right? They have the same hash. So it won't help if you increase the number of buckets here. Whatever the number of buckets, these strings, they have same hash, so they will go to the same bucket always. And we see that in this situation, our hash map degraded to linked list. And this, again, can be used as an attack, for DOS attack, denial of service attack. So if, for example, in Apache Tomcat, we store some session IDs in hash map, somebody can generate lots of session IDs with the same hash, and it will break this hash map in Apache Tomcat. The hash map will become a linked list, and yeah, everything will start to work very slow. And this situation was until Java 8. With Java 8, we have this improvement of hash table. Oh, people are laughing. Like, who sees this for the first time? Who like never heard? Oh, half of the people. Okay, it's great. It's good because like I'm biased. I think like this is a well-known fact. Everybody knows about it. So yeah, this is the trick. So when we have more than 8 collisions in hash table, in order not to risk the denial of service attack, Java hash map starts to treeify. So what we see here is actually a red-black tree. You see there are red nodes, black nodes. We will cover this later. But the trick is, if we like, most probably you are using something comparable as a key. You are using string as a key. So string can't be used in a tree map. So if we have less than 8 collisions, then sequential search, in the bucket will do for us. But if there are more than 8, then we're rebuilding it with the tree. And the price will be logarithm of n, where n is number of collisions. And yeah, you see there is an enormous memory overhead as well, because these green arrows, they are links as well, so they are occupying space. Okay, linked hash map. I'm afraid I'm running out of time, but yeah, let me maybe go faster. So we have linked hash map, and linked hash map in Java is actually a nearly ready LRU cache. So you can create a hash map and use it in a mode where when you put some element into hash map and there are more elements than a threshold, it will be removing the oldest or most unused element. It is in the standard library, and you can use it without any additional libraries in Java, which is good. In Java 9, we also have another type of a map, the immutable hash map. When you create the map with this builder map off, which is very convenient one, but not only it is convenient. If you thought that you are using map off and you get a hash map under the hood, then you are wrong. It creates a class called mapan. It's hidden, it's private implementation of map interface. And you see, it doesn't look like a hash map, like a standard hash map, because first of all, it uses the same array for holding keys and values. They are just interleaved. So odd numbers for keys, even numbers for values, which makes it easier to, which allows us to utilize CPU cache actually, because there is no memory fragmentation. And also it uses what's called linear probing when we have a number of collisions in HashMap. So it creates the first element, puts it into some bucket. When we have a second element for the same bucket, it just goes to the right and looks for a free space in the bucket space. So that when we have collisions, and for this key, for this bucket, the key value is wrong, we're just going to the right, looking for the correct key, which is actually more efficient way, because we're using arrays, not linked lists. Arrays are more efficient. Yeah, unfortunately, this works only with immutable maps, because when you try to think about how you should deal with deletion of elements from this map, and it can be somewhere here, right? So it can be troublesome. You need to rebuild things. So linear probing works well for immutable maps, and this is why in standard library they use it. Do I have 4 minutes late? 4 minutes left, right? Okay, concurrent hash map. Concurrent hash map before Java 7 looked like this. This was actually a set of maps, and each map was locked individually. And starting from Java 8, we have improved version of concurrent hash map, which looks like a normal hash map, but they are utilizing compare and swap operations on bucket list, and they are locking only the chain of collisions. Well, folks, I'm afraid I need to wrap up my presentation, but actually I just wanted to demonstrate the tree map also, which utilizes red-black tree, and an interesting structure called concurrent skip list map, which is navigable map, but it's lock-free. And this structure is most complicated in all the Java library. If you look inside its source code, you will see lots of references to scientific papers inside it. So, but what it does, it actually provides us navigable map interface, which is in turn lock-free. So, and it uses the skip list, and it uses random number generator at some point in order to take a decision about adding some nodes to this structure. So all this very interesting and exciting, I would say, but I have no time for demonstrations. But you have a link to my presentation. You have a link to GitHub. So please check out the JOL project. Please check out examples from my presentation. Please give JOL project a star, experiment, and send us your ideas. Maybe we should include more illustrations here in this presentation in the future. Thank you for listening. Thank you.